I hope you are doing well. My name is Mushtaq Walipur, and I'm a PhD student of computer science at the University of Waterloo. And today I'm the session chair for this session and the next one. The title of this presentation is Embedding in Natural Language Processing, and we proudly have Mohammed Taher Pilevar as our speaker. He is an assistant professor at Tehran Institute for Advanced Studies, and he is also an affiliated lecturer at the University of Cambridge. Taher's research is primarily in the field of natural language processing with a special focus on lexical semantic. Taher has co-instructed 4 tutorials on representation learning at main NLP venues such as EMNLP 2015, ACL 2016, EACL 2017, and NACL 2018, and co-organized 3 SEM-eval tasks and an EACL workshop on semantic representation. Taher has contributed to the field of lexical semantic with several papers, including 2 ACL Best Paper nomination 2013 and 2017, and a recent textbook on embedding in natural language processing. I would like to invite you to watch the videos and hopefully you enjoy it. Please prepare your question at the end of the session and we can ask the question directly from him. Perfect.
Hi there, this is Mohammed Taher Pilevar. I'm an assistant professor at Tehran Institute for Advanced Studies, or TIAS. Also an affiliated lecturer at the Language Technology Lab at the University of Cambridge. In this tutorial, I'm going to give a talk on embeddings in natural language processing. If you have some experience in machine learning, even if not directly in natural language processing, there is a high chance that you've heard of embeddings. You've probably heard it for word embeddings, but in this talk, you'll see that there are other forms of embeddings that are being used in natural language processing. This tutorial is like a quick overview of a recent book I have co-authored with Jose Camacho-Collados, who is an assistant professor at Cardiff University. The book is a broad review and synthesis of the literature on what we call embeddings in natural language processing. It starts with an introduction to semantic representation, or what we call embeddings in natural language processing, and it covers different types of works on word, graph, sense, and contextualized embeddings, the recent literature on that, and also the history behind that. The book also covers sentence and document embeddings, which I'm not going to cover here in this tutorial, but I encourage you, if you're interested, go read the book. The draft is online, and it's going to be officially published by Morgan Claypool Publishers by the end of this year. Here is the distribution of the slides over different topics I'm going to discuss in this talk. As you can see, there is a special focus here on contextualized embeddings. And the reason is that contextualized embeddings are probably the most recent form of embedding in natural language processing, and they are currently one of the hottest topics in natural language processing with a lot of interesting stuff happening. I have a few assumptions here. First of all, that you have some basic knowledge of NLP and you're familiar with machine learning, and you have some basic knowledge of neural networks and deep learning. Artificial intelligence, or AI, is undoubtedly one of the most important topics of discussion in the past decade. The goal here in AI is to create machines or algorithms that can exhibit intelligent behavior. By intelligence, what we mean is the kind of intelligence we humans show in our day-to-day life in tasks that we do routinely, like vision, when we look at something and recognize different objects in an image or in a scene, or speaking. We communicate with other people by means of language, or reading. We read a newspaper or an article and understand what's going on, and different other tasks like driving, playing card games, etc., etc., decision making. The kind of intelligence that is concerned with understanding natural language, especially in the text form, is the concern of a subfield of AI called natural language processing. broadly speaking, natural language processing can be divided into two sub-problems: natural language understanding and natural language generation. In understanding, the concern is to read a text and to understand the semantics behind that. For instance, to understand the message being conveyed by that text or the concept being described. In natural language generation, the concern is to convert a concept, an internal representation in the mind, and to express it through word sentences. So you have some concept in the brain and you want to express it through natural language. There are many challenging problems in natural language processing. I'm going to mention a few of them here. For instance, ambiguity is one of the biggest problems, one of the oldest problems in natural language processing. Human language is ambiguous in many different aspects. For instance, let's consider lexical and consider the word fly. Fly can be a verb and a noun. This is one aspect of ambiguity. The verb itself can have many different meanings. For instance, time flies, or the pilot flies the airplane, and many other meanings the verb can have, together with many other meanings of the noun fly. It is very easy for us humans to disambiguate or understand the meaning of a word in a given sentence or in a given context, but this is not as trivial of a problem for computers. The other challenging problem we have in natural language processing is common sense knowledge. For instance, consider this sentence: the tablet does not fit into my bag because it is too large. It is very easy for us to understand that it refers to the tablet and not to the bag. The tablet was too large that it didn't fit into my bag. To understand this, we need some common sense knowledge. This is a sort of knowledge which is not explicitly encoded in this piece of sentence or in this piece of text. And for this reason, it is very difficult for computers to make such inferences about common sense. Common sense knowledge is a sort of knowledge we gather by experiencing, by living this world from our childhood. And this is not the same experience that machines have when processing text. The other problem we have in natural language understanding is figurative language. We have a lot of idioms, fingers crossed, or I'm all ears, or when you use sarcasm in your expression. These are difficult stuff for computers to understand because the meaning, the semantics is not obvious from the text, the surface form itself. And in terms of natural language generation, the problems are symmetrical. Again, you have ambiguity here. You have a concept. You want to express it through words. It's a one-to-many mapping. There are many different words. There are many different ways of expressing that. And you have a giant vocabulary that you have to pick some words from to express your idea. And also word order matters, especially in languages like Farsi, which is kind of free word order. You can order words in many different ways and still make a grammatical sentence. And at the same time, you want your sentence to be fluent, for it to be grammatical and fluent according to the language you are generating your text. One of the most fundamental problems in both natural language understanding and natural language generation is semantic representation. The problem here is to represent the meaning in a mathematical or in a machine interpretable form for computers to be able to understand that. So the basic problem here, for instance, considering words, is to attach some meaning to different words so that the computer can make sense of the word it is seeing. Like, what is the semantics behind desk, pizza, library, and rain? For instance, consider the word library. To a computer, a library is nothing but a set of zeros and ones. Depending on the encoding, each of these characters is going to be represented by a few bits and bytes. And even if you store the whole Wikipedia on a computer, or tens of thousands of or millions of documents on a computer, and then you ask a simple question like, what is the capital of Iran? The computer will have no idea how to answer that. Even it will have no idea what the question means. because all it is storing is a set of zeros and ones that are not interpretable, not understandable by the computer. One of the oldest ways of representing meaning to the computers is what we call a VSM, or a vector space model. The idea is easy. Here, the yellow rectangle is a 2D semantic space, a two-dimensional semantic space, and we are placing words in this space. The placement is in a way that semantically similar words are placed in the proximity of each other. So for instance, you have train station here, rail and railways. In another place in this space, you have fruit, flower, seed, leaf, tree. In another place, you have education, university, and library. Here is another example. You have a set of animals here, birds, leopard, tiger, jaguar, etc. And in another space, another subspace of this space, you have concepts about flowers, about trees, or other related meanings. In fact, a word in a space or a point in a space is like a vector. So you're representing each word in this vector space model according to a vector. Here, for instance, it's a three-dimensional vector. And in fact, you're representing each word in the language with three numbers. It's a continuous vector of 3 dimensions. And you're representing all the words, let's say hundreds of thousands of words in this space. Usually semantic spaces are of 100 or a few hundred dimensions in practice. This is a more realistic example. It's been a 300 dimensional semantic space, or 300 dimensional embeddings, which has been reduced to 3 dimensions with 10,000 words in the space. And if we look closer here around the word arsenal, we will see that there are a set of semantically related words like playoff, like matches, like teams, like Barcelona, Manchester, Liverpool, champions, and other stuff. This is a small part of a space that contains the word related to arsenal. The way of computing these semantic representations or these embeddings is in fact a very simple unsupervised approach based on what we call distributional hypothesis, according to which you shall know a word by the company it keeps. So the idea is simple here. You try to model a word based on the surrounding words. So if two words tend to co-occur or appear with each other a lot of times in a given text, let's say in Wikipedia, then you will try to place them in their proximity, close to each other in the semantic space. And if two words do not co-occur with each other frequently, then the two words are going to be placed at far distances in the semantic space. You have probably heard of Word2vec. This is one of the most famous sorts of embeddings we had in 2013, and it kind of revolutionized the field of semantic representation. It's two very simple neural networks, two different algorithms called context bag of words and a skipgram. The idea is very simple. You have an input sentence in which the target word is missing, and you're trying to guess that target word, WT, based on the context. Skipgram is similar, but it's kind of reverse. Based on the target word, you are going to try to guess what was the context around it. It's a very simple neural network feed-forward with one hidden layer, but the training is very efficient. It enables the model to see a lot of text and to come up with very high quality representations in a very low dimensional semantic space. The Word2vec algorithms kind of revolutionized the field of semantic representation with a lot of new research happening after that paper. In fact, the papers do have around 40,000 citations in almost 7 years. And I'm going to mention a few of the subfields in which research is going on these days. One subfield is retrofitting of embeddings. So the basic idea here is that word embeddings are usually learned in an unsupervised manner and by just looking at text like the Wikipedia text. But we have a lot of lexical resources that are created by experts, by linguists, like dictionaries. How can we benefit from these dictionaries in order to improve unsupervised word embeddings? For instance, just to give an example, in a dictionary we might have a lot of synonymous terms for the word bus, like autobus, like coach, etc., etc. And one idea here is to benefit from the synonymous terms in the dictionary in order to refine the learned semantic space, like to transfer a bit the representation for coach towards what we have for bus, or maybe to introduce a new word that didn't exist in the semantic space like autobus according to the dictionary we have. Just to mention another area of research in semantic representation for words, an interesting topic is cross-lingual embeddings, and the basic goal here is to learn semantic spaces that contain words from different languages. From, for example, in this picture, from Farsi, English, Italian, and Spanish. And you expect semantically similar words across languages to be placed close to each other in this space. And it can enable many different applications that are cross-lingual, like machine translation or other different kind of cross-lingual NLP tasks. As I mentioned earlier, one of the biggest challenges in natural language processing is the ambiguity of language. And it creates problems in many different areas, including semantic representation. And usually word embeddings are not good at handling ambiguity because you have a single point in the space, a single vector for representing a word. The word can potentially be ambiguous. It can have many different meanings, including potentially unrelated meanings. And this can create many problems in natural language understanding and generation. Just as an example, look at this sentence and many different ways in which bow or bow can be interpreted. It can be a sheep bow, it can be a tie or a bow, it can be a music bow, or it can be other stuff. At the same time, we have fly, which can be the insect or the act of flying over the ship. And you see there are many different ways you can interpret a sentence. This is a toy example, but this is a real problem, the ambiguity. And in fact, sense representation and contextualized representation that I'm going to discuss here in this tutorial are kind of solutions to the ambiguity problem, and they are ways of improving word embeddings in terms of handling ambiguity. Just to elaborate a bit more on this problem, consider the word mouse. It can have many different meanings, including the animal, the rodent, and the computer mouse. The problem here is that many words in a language are related to the animal meaning, like dog, rat, trap, cow, and rabbit. And there are many other words that are related to the other computer-related meaning, like the keyboard, buttons, application, computer screen, and robots. The main problem here is that you are putting together words, the green words and the blue words, in the space that are not really related to each other. In fact, due to having an ambiguous word at the middle, you are making unrelated words, or you're placing them in the proximity of each other, which is an unwanted thing in the semantic space. So this problem is usually referred to as the meaning conflation deficiency of semantic representations, or maybe the triangle inequality. So you don't want the distance between keyboard and rat to be smaller than the distance between keyboard and mouse and rat. You want this distance, this z, to be much, much larger than x plus y. We will see in the coming sections on sense embeddings and contextualized embeddings that this problem of conflation of meanings is kind of addressed in both these approaches in interesting manners. As I said earlier, there is a huge literature on word embeddings, especially from the years 2013 to 2017-18, with tens of thousands of papers, a lot of research problems, and a lot of achievements, different approaches. And please read the book if you are interested in having more information on word embeddings and different areas of research in that. I'm not going into more details of that because I want to keep some time for contextualized embeddings, which is a much more interesting and much more recent topic. And there is a lot going on here. This takes us to graph embeddings. I'm going to provide a very high level, a very quick overview of the work in graph embeddings, especially from the point of view of natural language processing. There is a lot, in fact, in common between word embeddings and graph embeddings, especially from the point of view of the approaches that are used for their generation. Graphs are ubiquitous data structures. They are often the preferred choice for representing various types of data, including social networks, for instance, a toy social network here, with people being connected to each other by friendships probably, or word co-occurrences or semantic networks. For instance, here you have some ontological relationships between different words, like fish lives in water, whale is a mammal, mammal is an animal, bear has fur, cat has fur, etc., etc. And the problem is that graphs are not easily digestible by computers. They are not easily interpretable, especially for machine learning algorithms. And there is a high need for converting them or transforming them into a mathematical form. And by converting them, I would say, to some numbers that are easily processable by machine learning algorithms. For instance, what we have here is a very famous toy graph called the Zacchary's Karate's Club Social Network. It has 34 different nodes for 34 members of that club. And here the edges denote if any of this pair of members had any interactions outside the club. So the basic idea in graph embeddings is to convert, to transform this graphical notation, this graph notation with nodes and edges, into what we would say here a semantic space again, into an imaginary n-dimensional space in which each of these nodes is represented as a point in the space or a vector. A very common approach for converting graphs into embeddings is what we call a random walk based method. Just to describe it here, what we do here is to transfer the graph into a set of artificial sentences by means of a set of random walks. So for instance, let's say we want to embed this node in here. What we do is to set a number of random walks, like starting from here, going from there, going to another node in here, passing from here, and then going to here, and maybe stopping at this node here. So what we have here is something like an artificial sentence, starting from this node here. Let's say this is A, B, and we are interested in representing B. Then you have C, D, E, F, and this makes an artificial sentence with D, E, F, with 6 words, and we are interested in representing B. You will make many of such random walks in the graph, tens of thousands, in order to make many sentences in which you have each word occurring many times. And then once you have a set of artificial sentences, what you do is essentially similar to learning word embeddings. You'll try to learn an embedding for the word B by seeing the context. If the term B or the node B appears many times with with a node G here, then the two nodes tend to have similar embeddings. And that's reasonable because they are sitting in a distance of 1 in this graph. So probably the more chances of going from one node to another node in the graph, the higher the chances are for these two nodes to get more similar embeddings in the space or to be placed in close to each other in the semantic space. Two of the very famous algorithms or approaches for this branch of algorithms is called Deep-Walk and Word2vec, both based on random walks, and they are sort of adaptations of the Word2vec model to graph embeddings. Obviously, it's not surprising to see neural networks also playing a role in graph embeddings. So one other type of approach is called autoencoder based model. And the idea is again simple. You try to represent a node in this graph using the adjacency matrix. So you have a 1 in this column if there is a connection between a node and the corresponding row. And then you'll use something like an autoencoder in order to compress this representation, this large representation, which is equal in size to the number of nodes in the graph, into a very smaller representation, into an embedding for that node. This is the general idea behind autoencoder based models for graph embedding. Another very popular way of doing graph embeddings is called graph convolutional networks, or GCNs. Again, the basic idea here is very simple. You try to compute the embedding for this node, for the target node, by looking at the embeddings of the neighboring nodes. And in turn, you try to embed this node here in the neighborhood by looking at its own neighboring nodes and by trying to aggregate those embeddings. And usually different techniques in GCN differ in the way they aggregate the neighboring embeddings. Either they take the element-wise mean, or they take the average, etc., etc. And this process is kind of familiar in the convolutional neural networks, CNNs, and for the same reason, this technique is called graph convolutional networks. There is also a huge literature in natural language processing on relation embedding. Because usually knowledge bases you have in natural language processing, the graphs you have contain directed label edges. For instance, here you have the child of relationship or the born-in relationship, and you want to preserve the direction and the labels in your semantic space. So you want to have different directions for different labels, and you want to preserve this sort of relationship or this sort of analogy between different terms or different concepts from the original graph or the original knowledge base you are encoding. I'm not going into detail of this, but just to have an idea, there is a big literature on relation embedding, and the main idea here is to also embed in the same semantic space the directions and also the labels of relationships between concepts. This takes us to sense embeddings, which is a way of addressing the meaning conflation deficiency I talked about earlier in word embeddings. But given that sense embeddings are kind of replaced by contextualized embeddings, I'm not again going to talk much into the details of sense embeddings, and very briefly I'll just describe some of the main ideas here. The idea behind sense embeddings is to learn distinct representations for individual meanings of words. The problem we had with word embeddings was that it conflates all the different meanings of a word, different meanings that a word can potentially have, in a single representation. It conflates them all in a single vector. What we are trying to have in sense embeddings is to have distinct representations for the different meaning. For example, for the word mouse, we are trying to have a distinct representation for the rodent and a distinct one for the device. Again, there is a large literature on this with lots of techniques. I'm just going to briefly say the idea, the concept behind the two types of sense embeddings we have. One type is text-based, in which you try to see the occurrences of a word in a text and try to distinguish, try to cluster the different usages of a word according to the context, and then learn different sense representations for each cluster. So for example, here for the word cell, that can have different meanings: cell phone, prison cell, and the biological cell, etc. We can distinguish the context for the word and then learn distinct representations for each cluster of contexts. Another type of sense embedding technique is resource-based. Here is the idea is to benefit from existing lexical resources like dictionaries. In a dictionary, we might have different meanings for a word. For example, 5 different meanings for the word cell. And we try to exploit the information encoded here, like the synonymous terms, the definition, what we call gloss, or maybe usage examples of that word. And we try to exploit the knowledge here in order to come up with different distinct representations for the word. So just to say very briefly, there are two different types of sense embedding techniques: resource-based and text-based. This takes us to contextualized embeddings, which I would say is the new type of sense embeddings, which addresses many of the problems with word embeddings and some of the problems with sense embeddings. The idea here is that words are dynamic in nature. As we saw earlier, a word can change its meaning depending on the context in which it is used. So we need dynamic word embeddings as well. We need some embeddings, some representations for a word that can adapt itself to the context in which it appears. For instance, we need a representation for mouse, a vector for mouse, or a model that provides a representation for mouse that changes the representation based on the context in which the word is used. For instance, a different representation here for the computer mouse, and it again gets adapted to this new context here in which the rodent, the animal, is being used. Just to elaborate a bit on that, in a conventional model with word embeddings, what we call static word embeddings, the one that had the conflation deficiency problem, what we usually do is to go into an embedding space and take the embedding for each word we are going to use. For instance, we extract the embedding for the word cell, irrespective of the context of cell, and then pass that to the model to make some decision making, whatever task we have at hand. So we have the same static representation for the word cell, which is independent of the context. But in the contextualized embedding, or in the dynamic model, we also take into account the context. So the representation model not only takes the target word, but it also takes the context in which the word appears. And according to the context, it adapts the representation for the target words. It changes the representation it has from cell in order to make it more suitable for the context. For instance, here it's the biological cell. And then it passes that dynamic embedding, which is generated on the fly according to the context, which is much more suitable for the model to make a good understanding of the semantics behind the input. One of the earliest models in contextualized embeddings is called ELMo, or embeddings from language models. The basic idea here is to take the internal representations of a recurrent neural network, an LSTM, as the intended representation for the target word. So instead of taking the static embedding for the target word, what we do here is to take the representation of the context encoded by an LSTM as the representation of the word. It's like having the context representing the target word. There are some details here, like we have a bidirectional LSTM, and the training procedure has some details which I'm not going into the details of, But the general idea here is to represent the word as its context. And that's how we contextualize a word according to the sentence or the phrase in which it appears. A more recent technique, which is much more popular than ELMo these days, is called BERT, Bidirectional Encoder Representations from Transformers. As you can see from the name, the basic idea here is to make use of transformers, the transformer architecture of neural networks instead of the LSTM or the RNNs. And this brings about a lot of advantages, like it can enable better parallelization, so much more speed up in terms of GPUs, and it can enable training on much larger data sets. And other stuff like long range dependencies are enabled by this sort of transformers representations because all the sentence is input at once, and the model is able to look at all the other words in the sentence at the same time in order to understand a specific word. The fundamental building block of a transformer or the BERT model is a mechanism called self-attention. It is in fact self-attention that enables BERT to capture long-range dependencies between different words and to make such an efficient processing of the semantics of a sentence. Let's have a look at a toy sentence in this nice demo provided by Hugging Face. The input sentence is the animal did not cross the street because it was too tired. When we humans read this sentence from the beginning to the end, when we encounter it, it is easy for us to understand that it is referring to the animal, and it was the animal that did not cross the street, and it was the street which was being crossed, etc., etc. We are making some relations between pairs or between among different words in the sentence, and that's the way we understand the message or the semantics or the meaning of a sentence. In fact, this is the same idea which is being handled by the self-attention. For example, just to give you some reference, because there are many different details here, like different layers we have, different heads we have. But for instance, when looking at the word it, or when processing the word it, the model is also looking at the word attention, and is also attending to the word animal, as you can see by the edges here. And it shows that the model is capturing some sort of relationships between these two words in order to better understand what it is referring to. Or maybe equally for the word street, as you see, it is highly related to crossing, or crossing is highly related to did not, as you can see here. And these are the sort of relationships that we usually make in our understanding. When we read a sentence, we make in our interpretation in order to understand the semantics of a sentence. And the same idea is being tried to be handled by this self-attention mechanism. The main training objective in BERT and many of its derivative models is something called a masked language modeling, or MLM. The idea is that in the input sentence you cover a word or a number of words, and then you ask the model to guess what was the masked word. So let's say you have 10 words, you mask 1 or 2 of them, and then at the output time what you ask from the model is to guess what was the word in this place which was masked or covered at the input time. And it is very interesting that with such a simple objective, the model is able to encode far more complex semantic and syntactic knowledge, which we are going to see a few examples in the rest of this tutorial, which makes it very interesting. Just to give you some impression on the syntactic abilities of contextualized embeddings and how far they can encode the syntactic knowledge in their semantic representation, I'll give you an example here. Here is a constituency-based parse tree for the sentence. So this parse tree is a tree structure that reflects the syntax of an input sentence in a language, here the English language. And it is very interesting that in a paper last year, Hewitt and Manning found that using a simple transformation, it is possible to extract the syntactic parse tree of a sentence from BERT's representations. And this is very interesting because in the training objective of BERT, we did not have anything about the syntax or anything about the dependency parse tree of a sentence. What we just had was the mask language modeling, and it looks like that the model has to encode this sort of syntactic knowledge about the language in order to predict a masked word, which is very interesting with that respect. In fact, here we have the gold parse tree of the sentence on top, the black one, and the one in blue, which is predicted by BERT, which are very similar in terms of their structure. And it looks like that without providing an explicit training objective for BERT, it is encoding a lot of syntactic knowledge in terms of dependency parse trees in order to be able to succeed in the mask language modeling task. And to give you an idea about the semantic abilities of contextualized embeddings in terms of distinguishing different meanings of a word or capturing sense information, here is an illustration by Cohen et al. From last year, showing that for the target word die, without providing any explicit information or without asking the model to learn distinct representations for different meanings of this word in different languages or in the same language, the BERT model is doing a very good job at putting representations at distinct places in the semantic space. So for example, for the German article die, we have some representations for the word appearing in context at this place in this semantic space. And for the verb die in English, if a single person dies, we have some representations at this part of the space. And if multiple people die, we have some distinct representations at a different location in the space. And in a far distance in the space, we have some sentences where die is being used as the playing die. And in fact, the model is doing a very good job in distinguishing different meanings of a word. And it is not only visible in terms of this kind of visualizations, but in terms of the semantic NLP tasks we have that need a lot of semantic knowledge about different senses of a word. The interesting fact here is that contextualized embeddings, or specifically BERT and its derivatives, have gone much, much further than just semantic representations. In fact, now they have conquered most of other tasks in natural language processing. In a process called fine-tuning, you can easily modify the input sentence to the BERT model and do some slight modifications at the output level, and then show the model some training instances from the target task. And in this way, adapt the model to many different tasks in natural language processing. For instance, for sentence pair classifications or single sentence classification tasks like question answering tasks or tasks like named entity recognition or many other different tasks in natural language processing. And the interesting fact here is that with a single model, you can obtain very good results in those target tasks, usually state-of-the-art results that outperforms many targeted specific models that you had for these specific tasks that were very complex, that were very tuned for that specific task. But here you have a one-for-all model that encodes a lot of semantic and syntactic information, which is suitable for many different target tasks, and it can outperform many of the existing targeted specific models in those tasks with very slight modifications, with very slight fine-tunings to those target tasks. And this is what makes contextualized embeddings, especially BERT, much interesting, and one of the most interesting and one of the hottest topics in the current research in natural language processing. For instance, here is the leaderboard for the GLUE benchmark, which is a standard benchmark for evaluating different tasks in natural language processing. If you look at the top models here, you see that many of them contain the word BERT, like they are either some sort of ensemble models that include BERT, or there are some modifications of BERT with different training data or training objectives, many of them. And what is interesting here is that the Word2vec model, which used to be a state-of-the-art till a few years ago, is now something at the very bottom of the table. So you see the overall results for the SIBO or the SIBO model of Word2vec is about 58%, where the state of the art is now reaching the human level performance, which is about 90%. Similarly, for a more recent benchmark called the SuperGLUE, again here all the models, as you see, have some sort of BERT in them. There are some derivatives of BERT, like Roberta, like Albert, like Electra, etc., etc. And I'm going to talk about GPT-3 in a few slides from here, which is one of the hottest topics and one of the most interesting recent advancements in natural language processing. But just to give you an overall impression about natural language processing, the field is very much now affected by transformers and by BERTs and its derivatives, and all the achievements and all the impact it has had on different areas of research in natural language processing. The general development trend in the past few years has been to go for different derivatives of the BERT model, usually with larger architecture. So for example, here we have the BERT large with 340 million parameters. Then we had GPT-2 with over half a billion, 1.5 billion parameters, or another version of it that had 8 billion parameters, or a more recent model from Microsoft called TNLG with 17 billion parameters. Usually these models are all using transformers and are similar, but they have a slight modifications in the size of the model, in the number of layers they have, in different architectural choices they have in the models, or in the data they use for the training. Like for Excellent, we have a much bigger, much larger training data for training, or in the training objectives they have. Either they have the next sentence prediction, or they do not have it, or other stuff which I'm not going into details of which. GPT-3 is one of the most recent models of the type. It comes from OpenAI, and it is very giant in size. It has 175 billion parameters, which is more than 10 times the largest model we had so far from Microsoft, which was TNLG. It is much larger than their earlier model, GPT-2, and it's been limited so far, so it's not freely accessible to the community. Limited access is given to a number of people to test GPT-3, but even this limited usage has shown a lot of potential and a lot of interesting stuff, about which I'm going to talk in the next few slides. For instance, this is a snapshot of a conversation by an agent which was enabled by GPT-3. You can pause the video and have a look at the dialogue, but in many different ways this is interesting. So the amount of intelligence the model is showing in the conversation. So, and at some points the conversation is getting very philosophical. So for example, the AI is talking about the hierarchy of complexity, or it's talking about God, and etc. You can pause here and have a look, and this is really interesting. This is another example of a model enabled by GPT-3, this time a pattern matching model. So here you have a number of states with their population, and then you ask GPT-3 what is the population of Michigan, and it tries to look at that in the knowledge it has, or that for Alaska, and it finds the population for that. And consider that there is nothing about this in the training objective of GPT-3, or there is nothing explicitly encoded about the population of different places, or such information is in training. Or the date it was founded, it can find that and recovers that. First, it can find the relationship between a state and a foundation date, and then it can retrieve that for that specific state. Or we can ask it to learn summation here between two numbers. Again, remember that there is nothing about adding two numbers in the training objective of these models. Or you can have the relationships between persons' names and the employer, between different people like Jeff Bezos and Amazon, and it can find that for different people, or the Twitter account for different people, it can find it for Michael B. Jordan, for example. Or here is a simple app builder, where again you describe something you want, a header that says mood tracker, then a button that says happy, sad, and sleepy. When I press a button, show text that says, right now I'm feeling X, where X is my mood. So see, there is some complexity, not only in the description that the model has to understand, but also in the references that are given in this description. And the model generates the code for that, and the code nicely works. So you add here that where X is an emoji. You want an emoji for the corresponding button we have. And the model generates the code with the emojis. When you press a button, it shows the corresponding emoji for you. This is another interesting demo of HTML code generation enabled by GPT-3. Here you describe a layout you're wanting to be created, like a Google logo, a search box, and two light gray buttons that say search Google and I'm feeling lucky. That's a description you provide, and the model generates the corresponding HTML code for you. And then you ask a padding between the two buttons, it generates that padding as well. You just provide them with the descriptions, it comes up with the code. Or at the search box, you say you want a white search box. It adapts the code according to this description. Or another related demo of when you describe a layout and it generates the code for you, like a button that looks like a watermelon, or a large text that says welcome to my newsletter, and a blue button that says subscribe. So you see, you just provide descriptions and it provides the HTML code for you here. A button for every color of the rainbow. So it has to understand what is the rainbow, what are the colors in it, and also how to generate the code for buttons. There are many different sorts of stuff that's going on here. A table of the richest countries in the world with the columns names and GDP. So here the model makes some small syntactic mistake, which is being fixed manually. And yes, the table with the richest countries according to their GDPs. The ugliest emoji ever. According to GPT, that's the ugliest. 5 buttons, each with a random color and a number between 1 and 10. The color did not work, or a simple landing page. A header that says I love AI, and an emoji and a button with a brain emoji. And there's a lot going on here, like let's have a look at another one, like a button with the color of Donald Trump's hair. So it has to understand who is Donald Trump, what color is his hair, and generate a button for that. There are a lot of interesting stuff like this. You can go to the Twitter account of Sharif and see more examples like this. Here is another demo that shows you can create regular expressions by just providing descriptions enabled by GPT-3. So in this demo, right, like find a valid URL that starts with HTTP or HTTPS, and then you provide an example for that regular expression you're looking for, and the model generates the corresponding regular expression for you without having any internal encoding or any knowledge about, explicit knowledge about how to do regular expressions. Or find an uppercase word with length 5, and this is an example for it. And it nicely finds the corresponding regex for you. And what makes this interesting, to stress on that, is that there is nothing in the training objective of the model about encoding this source of information. And this provides a lot of potential for different areas like program synthesis to many different applications you can think of. As a last example of the sort of demos that are enabled by GPT-3, here is a demo that generates Keras code using descriptions you provide, like build a model to classify images into 5 groups. The dataset has 25,000 images with an input shape of 500 into 500. And the model generates a code, a Keras code for you. It's a sequential model with some layers, and at least by looking at the model, it is a reasonable model with some convolutional and max pooling layers in it. As I said earlier, there is a lot of discussion on GPT-3 nowadays with a lot of interesting achievements and a lot of interesting possibilities that it has opened. But one interesting observation about this is that on a task called word in context, which I'm going to describe in short, the model is performing no better than a random baseline. And this is surprising given the fact that the model is so intelligent in terms of semantic and syntactic knowledge and in pattern matching, while it performs so poorly on a task called word in context. The word in context task is in fact a dataset that I proposed with Jose Camacho Collados last year. It's a simple binary classification for humans. You are given a number of instances in the dataset with true or false labels. Each instance has a target word, like bed, that appears in 2 different sentences. There's a lot of trash on the bed of the river, or I keep a glass of water next to my bed when I sleep. And the model has to identify if the target word is being used with the same meaning or not. It's a simple task for us humans, but a difficult task for computers to distinguish the different meanings of a word in different contexts. The task is a part of the SuperGLUE benchmark, which, as I said earlier, is one of the standard benchmark nowadays to evaluate different natural language processing models. And there is a lot of evaluations going on this task. And there are, in fact, a lot of good models, like we have some recent research from Facebook, Allen AI, and Stanford or Google that perform pretty nicely on the data set and get close to the human performance, which is 80%. But it is very surprising to see that the GPT-3 model which is so much probably better than all these models in terms of different NLP tasks, falls so short of doing well on this word in context task, which opens up a lot of research questions and a lot of interesting stuff in the future. So this wraps up my discussion about contextualized embeddings and embeddings in general. There is a lot going on these days on contextualized embeddings, much more than what I discussed here. And the field is rapidly changing with a lot of new interesting stuff happening, which I encourage you to go and check if you are interested and to keep posted about that. But before I conclude this talk, I'd like to talk about some ethical issues around embeddings. So the problem with most supervised machine learning models is that they are usually trained on human-generated data. So it is inevitable for them to encode the implicit stereotype biases we have, like the gender, racial, ideological, or other sorts of biases we have in the data, unless we take some explicit measures in order to prevent this. And the problem with this is that machine learning models have now passed the experimental stage, and they have now entered our lives in different areas like medical testing, like online advertising, like criminal justice. And this is no more good at all if there are such implicit biases in them, because they can even reinforce such biases in the communities. There are many examples in this area, like in terms of face recognition models, there is a lot of discussion on the existing bias against women and darker skins when we have gender classification tasks. Or there was a famous study by ProPublica on a risk assessment tool that was widely used in the criminal justice in the States. And it was found that, well, the tool was being used in order to predict the probability of a defendant to commit a crime in the future. And it was found that the tool was heavily biased against African American defendants, probably assigning them much higher chances of committing a crime again. Or there was another topic of discussion about Facebook's famous emotion contagion experiment, which was sort of a data science experiment in which which involved manipulation of people's feed in Facebook in order to see what are their reactions or to study some of their behaviors, which raised a lot of ethical issues about people's privacy and related stuff. But coming to the embeddings, there are some existing biases in embeddings as well. So in a seminal work, Bulukbashi et al. Found that there are many such stereotypical biases encoded in very existing models that we use in a lot of models, in a lot of systems these days. For example, in the pre-trained Word2vec models. So what they did was to check for the closest occupations for the two pronouns, he and she. And here are the results we're looking at. As you can see, for he, we are having occupations like philosopher, captain, architect, financier, magician, maestro, etc. But for she, we have homemaker, nurse, and librarian, nanny, etc., etc. And this shows a strong bias against women, which is encoded in the embeddings. Or another observation they had was that gender stereotype analogies exist in the space, like we have sewing, carpentry, we have registered nurse versus physician, we have housewife versus shopkeeper, we have nurse versus surgeon, etc., etc., etc. And in fact, this has started a new area of research called debiasing, which looks after removing these encoded biases in word embeddings. Yes, this was just to give you a very brief introduction on debiasing on word embeddings and the existing issues on the ethical matters around word embeddings and machine learning in general. Well, this concludes my talk on embeddings in natural language processing. I tried to provide a high-level introduction to what semantic space is and what are the different types of embeddings that are being used in natural language processing. I hope you found this useful, and if you have any questions, I will be available at the question and answer session. Take care in this crazy COVID periods.
Okay, perfect. This was a very good presentation from Mohammed Taher. Thank you so much for your presentation. I think we have many couple questions. I can say, you have to, you're going to be busy a bit. Yeah. So let me actually start with the first question. So the first user actually asked that have the embedding methods such as Word2vec and BERT has the same goal? Do you think like that? Yeah. Please go
Let
ahead.
me test if you can first hear me.
Yeah, perfect. It's
Okay,
perfect.
yeah.
Go ahead.
Yeah, salam to everybody. And yeah, this is a good question. So in fact, all these models are language models. And in a language model, what you're trying to do is to complete an incomplete sentence or guess a missing word in a sentence. And all these language models are doing the same task and are having the same objective, but with different formulations. Like in Word2vec, as I said in this talk, we have two algorithms. In one of them, you are dropping a word from a sentence and you're trying to guess that at the output. And in the other one, it's a reverse procedure. Like you have a word and you have to guess what are the possible contexts, what are the possible other words that can appear beside that. It's the same process, in fact, in BERT with some slight modifications. Well, the architecture is very different. Therefore, you need to have some changes to the objectives as well. But the main idea is the same. So the main objective in BERT is something called a masked language modeling or MLM. And the idea is very similar. You have a sentence, you drop a few words from that. Essentially, you drop 15% of the words in that input sentence, and you try to guess that at the output. So what was the word that I just covered with my hand? And there are some other objectives, but they are secondary. The main objective in BERT is also a language modeling objective, as I said. So yeah, all of these models are similar in terms of the goal, if you want to call it an objective, but they are dealing with that differently, with different neural networks, different ways of formulating that objective.
Okay, perfect. Let's go for the next question. Actually, this one is quite a big one. So the Hossein Amir Khani actually asked that we humans understand the meaning in a seemingly effortless manner, a system I type, if you will. But the state-of-the-art models in NLP embedding are really huge, and they also need for far much training data, even though unlabeled than humans. Do you have any idea what's the reason behind this huge gap? Are AI in the right direction in your opinion? Do you think that, yeah? What do you think?
Yeah, that's a great question. Hi to Mr. Amir Khani. Well, let me challenge this a bit, the assumptions you made first. I do not think our brain is much smaller than the networks we have in terms of parameters. In fact, it's orders of magnitude larger in size. And secondly, it's not an easy process for us humans to start speaking. In fact, it takes many months from a baby with a very active brain, maybe 2 years to start making very simple sentences. And during all this time, the baby is experiencing the world. And I guess the common knowledge about the world the baby collects makes a difference in the preceding years. In fact, we have the same problem in vision, as you're familiar. So if I show you a photo of a new animal, just a single photo, you'll probably be very confident about recognizing the same animal in any other number of examples. Maybe just one or two examples are enough for a human. But we know that this is not the same for machine learning algorithms. One of the reasons being that they do not usually have this 3D imagination in their mind. But we have the same problem here. I think the analogy for this 3D imagination is the common sense knowledge that we do not have here for language. In fact, the neural network is just provided with a set of training examples, just a set of sentences, whereas we humans have a lot of background in our life, so we experience many different stuff, and not just speaking, but also seeing different concepts and having different descriptions for them in our brains. Yes, I think that's the most I can provide. It's a difficult question, I admit.
Yeah, sure, perfect. Just to add to your comments, actually, GPT-3 has only, our largest machine learning model has only 175 billion parameters. Let's say these parameters are synapses, and human brain has around 100 plus trillion synapses, which is quite much larger than the, or even our largest model. So for the next question, what's the solution for representing unseen words in the test time? Will be a method such as zero-shot learning useful for representing such words?
Yeah, that's another good question. So it was more of a problem for static embeddings like Word2vec, because they used to learn word representations. We had a representation for a single word, and it was very possible to encounter a word during the test time for which we do not have any embedding in our dataset, in our database. But for the case of the more recent contextualized models, it's less of a problem. And one reason behind that is that we go here for subtoken representations. So we usually split each word into subtokens, into a set of characters based on some statistical measures. And essentially, in a language that might have hundreds of thousands of words, unique words, what we learn is just a set of dozens of thousands of subtoken embeddings. And it's less of a problem here because any new word can be split into some existing subtokens, and we can cover that by just aggregating the embeddings we have for those subtokens. So here, what we usually refer to zero-shot is usually in a classification problem or in any other NLP task for which we do not have any training data, I mean, in terms of labels. And yeah, there is a large literature there, which I cannot talk about now.
Sure. For the next question, what about Persian language? Semantic representation for Persian. And are these models suitable for Persian language, and have they been applied to Persian language as well? This is a question by Nasim Tohidi. And do you think that we are going to have, I think, maybe, a good representative data set at least for Farsi?
Yeah, that's another good question. So I can divide the answer into two. So one is, yeah, we have pre-trained embeddings for Farsi language. We already have two BERT-based models. One is from the University of Turku, and the other one is from, I don't remember the name, but the model name is parse BERT. And despite the large amount of GPU and compute unit for them, but we have already models for the Farsi language, and they are performing very decently in different benchmarks. That's one part, and as I said, yeah, they perform really much better than conventional techniques like Word2vec, also on Farsi. The other fact is that These contextualized models are very effective at learning cross-lingual embeddings. So you have a space, like we already have a pre-trained model for BERT containing more than 100 languages, including Farsi. And it includes all the words in all these 100 languages. And the very nice thing here is that you can transfer your knowledge from a language like English to Farsi. For instance, you can have training data for sentiment analysis, for classification, for named entity recognition in English. Train a model in the English language on that data set you had for that language, and then use it for Farsi. And surprisingly, it performs really good, usually much better than the existing models for the target language, including Farsi.
Okay, cool. Do you know any method for detecting the irregular or high-skilled forgery text?
I'm not sure if I understand the question, but if it is like a sentence that doesn't look fluent, like doesn't follow the
Actually, he
grammar.
means that, you know, he's trying to give you some sort of information about any kind of fake documents that are, you know, perfectly, you know, faked, maybe authentic documents.
So by fake, we mean it's been automatically generated by some machine?
Oh, no, some, let's say some human person just, you know, forge a specific, maybe government document. So you just, you know, it seems to me, even for automatic, maybe he is asking, yeah.
Well, I still do not understand the question if it has something to do with the fake news and stuff, or I don't know what a forged text means in this context.
Okay, yeah, if the guest three actually asks his question,
Yeah, we
maybe
can continue
later we
offline
can,
if
yeah,
you'd like.
absolutely. Yeah, sure, perfect. The next question is by Mohammed Haidari, and he asked, can we say no? It is time to goodbye to traditional word embedding methods like Word2vec or GloVe with the presence of transformers, I think, yeah.
Yeah, that's another good question. So I think from the research point of view, yeah, my answer is yes. So if you have a paper nowadays with no comparison to BERT or some derivative of that, I would say there is no chance for having that paper in a top tier conference in NLP, for good or bad. But in terms of applications, I think there is still room for them because they are usually much lighter, much speedier than contextualized models. And they are especially good for mobile devices or for scenarios where speed matters. And I think, yeah, we are not going to see that soon, at least from the applied side of it.
Okay, I see. Babak Sultani asks, addressing the social biases needs some kind of judgment, right? How can a model judge each batch of the training data to be healthy or biased? It's a complex problem that even we humans don't have its answer.
Yeah, that's another good question. So if this refers to the biasing, to the ethical issues at the end of this talk, yeah, in fact, the problem is much more severe and much more complicated than what I discussed from that paper. Usually the biases that are inherent in human text are much more complicated. It's not like having just a gender bias that you can address by transforming the space or etc. In fact, there is a recent paper on 2020 by Yov Goldberg and some of his students that tries to look closer into this problem. So if you're interested in having more information about this, I would refer you. I think the first author is Hila Gonen, and the last one is Yov Goldberg. I don't remember the middle authors.
Oh, cool.
But yeah, that's true. So it's a much more complicated problem than what I just presented. That what exists now in the literature, because it's a very new research area, I would say is maybe just 1 year or less than a year that we have a new track in ACL conferences dedicated to ethical and biases issues.
Nice.
Yeah.
Could you please explain about the position embedding? Mariam Asadullah asked.
Yeah, so just to say it briefly here, So one problem with these transformers is that you input all the sentence at once. So you are giving all the words of a sentence to a model like a feed-forward network, and the model will have no idea about the order of the sentence unless you provide some extra knowledge about the position, the relative positions of words in that sentence. So positional embedding is some sort of a mathematical, automatically generated embedding that you add to the input words in order to make the model understand the relative positioning of words in the sentence or to make it sensitive to the order, if I just want to make it brief.
Yeah, thank you. So Masa Rodimer asked that what's the best solution to deal with words such as so and nice? I think she means that any kind of form that was deformed, for example, for yeah. Go ahead with it.
Yeah, that's a good question. So in fact, this might look funny, but this is a really serious problem when you deal with social media text, like text from Twitter. For some of them, it's easy, like for the examples you provide. Maybe you can look for a heuristic or some simple regular expression to address this, like replace all the occurrences of repeated characters with just one character or two and check if that makes sense in that language. There are some ways because we need that when we do a lot of tasks on social media texts, and there are much more complicated problems than having this type bad spellings. We have problems with syntax, we have problems with semantics or sarcasms, idioms that we've not already seen. There are some works on that, but there is no one solution that we can address all these things together.
Okay, nice. When we look at the clusters of the vector representation of words, do they necessarily consist of synonyms? I mean, are there different relationships between words being captured by clustering, as by Mohamamd Farshidfar? Yeah.
That's another good question. So it depends. So we can have also antonyms nearby to each other. And in fact, this distinction between antonyms and synonyms depends on tasks. So for example, one might say that man and woman, sunset and sunrise, south and north are antonyms, but one might say that they are very related, maybe kind of synonyms. It depends. And in fact, you can play a bit with the objectives of these language models to adjust this. For example, in Word2vec, if I remember correctly, if you make the window size larger, it tends to go from the similarity end of this spectrum towards relatedness. So it tries to have student together with university instead of having a student with teacher or I don't know, other stuff that are similar in concepts to student. And in terms of other relationships, there's also a literature on that. So there was a very old example with Word2vec, which is in fact overused too much. And well, the example is that if you try to make a vector from king to queen, then you and if you try to make the same vector from man to woman, the two vectors are parallel and identical to each other. And in this way, you can encode a lot of different analogical relationships in the learned embedding space. This is true to some extent and not true to some other. But there is something. So some sort of relationships other than synonymy are encoded in these spaces, especially in the contextualized spaces. As I said in this talk, Hewitt and Manning found that a very simple transformation of the relative positionings of words in this space can estimate the syntactic parse tree of a sentence to a very good degree of accuracy. And the syntactic parse requires a lot of syntactic knowledge about a language, which we have nothing about that in the objective of these models. So this shows that for the BERT model, just to predict the word which was covered in the sentence. So I cover a word and I ask you to guess what was the missing word in the sentence. In order to do that properly, you need to also learn some knowledge about the syntax of a language and other stuff. And this is one of the interesting observations with these contextualized models.
Nice, thank you. Barry's question is GPT the state of the art for unseen word representation? How do graph convolutional neural nets do in comparison? Yeah.
Well, we don't know much about the unseen word representation. I don't think there is much because it's, as I said, it's not that much of a big problem nowadays. And we don't know much yet about GPT-3 because, as I said, the model is not released yet. We just have a set of demos and the original paper. So it's not yet entered to the research area where different people can test different algorithms and try that on different downstream benchmarks. And so I do not have any answer to either of the questions.
Okay. Would you have any attention to pronunciation, because we have some similar word with a different meaning in pronunciation?
No, unfortunately not. So in natural language processing, you usually only take as input the characters and no other information like the speech or pronunciation, which might be very useful, but that's missing.
Yeah, but because it's actually hard to, combine different kind of data set together, maybe.
That's true. Yeah.
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 In the cases that we need sentence embedding like QA tasks, do you suggest using previous sentence level embedding like InferSent, or it is better to use word level embedding and make a new model on our dataset for achieving sentence level embedding? Asked by Pfizer.
Well, it's a difficult question. I don't know. It depends on the specific task and the data set. So I do not have really, an answer that I would guarantee to work. But there are different sentence embedding techniques that are state of the art, starting from universal sentence encoders to Contextualized. There is a literature on that, but I cannot answer this question specifically with a model that I can guarantee that works well in a benchmark. I'm not sure.
Okay, nice. Masaradimir asks, for finding similar documents, do you suggest word embedding or document embedding?
So, well, I definitely do not recommend word embeddings. So, because they are not designed for that task, and especially so, in fact, document embedding is one of the difficult problems in natural language processing. How can you encode a whole document that has a lot of words in it, a lot of different concepts, probably a lot of different topics? How can you encode it in a single vector, in a single point in the semantic space? Apart from this question, if we have an answer to this or not, word embeddings are usually not good for this task. So if you take all the embeddings of words in a document and try to aggregate them somehow, like if you try to take their centroid or average, it will not work.
Actually, that was a great answer. So, related to this question, do you think word embedding is enough, comparing, for example, to sentence embedding or anything similar to sentence BERT or all the, things that are related to that one? Do you think word embedding is enough for us?
No, definitely not. As I said, word embeddings are usually good for sentence level texts. As we go larger, as we go for paragraphs or documents, any sort of word embeddings are not the solution because their objectives are different.
Okay, nice. How do you see
usually when you have a document embedding or a paragraph embedding, they usually back off to word embeddings, but the way they combine this is smarter than taking the average or taking their centroid, because different words in a document have different prominence. So if I can call, so some of the words are more prominent, they have more semantic value to them, and some of them have less prominence. And the other difficult problem is how to combine different concepts which are not that much related in a document. So I do not know much about document embedding, and in fact, there is the literature for word embeddings is much larger than that for document embeddings.
Yeah, perfect. So, generally, how do you see the future of embedding? Do you think that I can say maybe, is this the path? Is this the correct path is this the thing that we are going to take in the end?
Before this, like a few years ago, it was a natural language processing with a subfield called semantic representation with embeddings. But now it's one natural language processing, and I would say one model for it, which is the contextualized models. In fact, this word embeddings has sort of conquered all different tasks in different areas of natural language processing. And if I just want to repeat, the same BERT model usually performs much better than all these sophisticated models for specific tasks, like for word sense disambiguation or a downstream task like that. We used to have a lot of features, a lot of different technical stuff, a lot of linguistic features, like 50 years of research into that, and then a single BERT model that has nothing to do about that target task enters the scenario and outperforms all those models, which makes things complicated. So I think the future of natural language processing is very much tied with semantic representation or these contextualized models. Well, in fact, it's been the same for the past few years, and I think it will be the same for the next couple of years. The only difference is that now people are now trying to focus on making larger and larger models with the hope of getting higher and higher in the benchmarks. But soon we have to realize that we have to go also in the other trajectory. We have to go for smaller models that can effectively do the same tasks faster and with less compute.
Nice, thank you so much for your answer. Hadi Khoja says, did anybody figure out the adversarial attack on embeddings? Is it possible to have text modification that changes the conceptual embedding decision?
Yeah, that's another very good question. Well, in terms of the adversarial attacks, we do not have that much of a work here in natural language processing as we do in vision. Because the scenario is different in vision, you have a photo, you can modify some pixels or change a part of that picture and try to make the model go wrong. But in terms of embeddings, it's a bit different because if you modify a word, then it's not the same word, it's another word or it's a typo. And maybe you can reorder the sentence or add a word to it. There has been some work in the latter type I just mentioned. So for instance, you have in a question answering task, you have a paragraph, then you ask a question and the model has to find an answer for it. There are some works in the literature that try to add a few words at the end of that paragraph, maybe some random words that do not even have any meaning. And the model makes a mistake in finding the correct answer in that paragraph. But as I said, there are just very few works in that direction because the scenario is very different from vision, as I said.
Okay, nice. The last question from the participant is, Microsoft released the code BERT recently. Can you briefly explain it?
I don't know about that.
Yeah, me too. Me neither. So, actually, I have maybe two questions for you. We are out of the time, but if we just, actually can wrap it up very soon. So as the first question, you mentioned that we can extract the knowledge of the GPT-3, for example, and it's really useful. But as you just mentioned, it's quite hard to maybe update GPT-3 knowledge somehow because we don't have really any kind of control over the whole knowledge. Do you think this is going to be useful or something for us in the end? Because this is the problem with deep learning, not necessarily with the language models. But what do you think?
Mm-hmm. Well, that's a good question. So maybe the more general question is how the research will look like for the case of GPT-3, because even to load the model, you need, I don't know, 128 gigabytes of RAM, which many of us do not have in academia. So I don't know how the research will look like for GPT-3. And the question you had, well, it's been shown that GPT-3 is more of a pattern matcher than having a knowledge-based background, maybe. it's hard to answer this question, and I'm not sure how the scenario will be like if they release a GPT-3 and if many people will be able to do something with that. I guess not many institutions or not many research groups will be able to even fine-tune that, let away the updating, you say, or the training, which I had in the slide that the training cost for this model was something like $12 million.
Yeah.
Imagine that.
Yeah.
So I don't know how the future will look like for research on GPT-3.
So as the last question, it's quite a bit a philosophical question. Do you think if we manage as AI scientists to understand the languages, is this can lead us to maybe artificial general intelligence somehow?
Well, that's a good question. So, and it's a difficult one. I think this is one of the most difficult problems in AGI. So in fact, probably if you can address this problem of understanding natural language, probably you've solved most of AGI. But this is one of those kind of philosophical questions to which I'm not ready to answer, and it's really difficult to answer.
Yeah, it is. It is really difficult. So yeah, thank you so much for your time. It was a great presentation, and it was absolutely a great Q&A. Yeah, sure. Thank you so much, and I hope that you have a great day. Thank you so much for participating. Yeah, for being here. Yeah, thank you. Bye.